Right, so I'm Abhisek. I'm going to be talking about agents that can see, talk, and act. So specifically, I'm going to talk about 3 papers today, and I might squeeze in 2 other papers at relevant parts, but I won't go into details of those 2 other papers. So let's start. So this is work from a couple of years back. The main goal of Visual Dialog is that we want to build agents that can see and talk. So to give you an example, for an image like this, a machine might generate a description such as a man and a woman are holding umbrellas. A human might then ask a follow-up question like, what color is his umbrella? To answer this, the machine has to understand which person the word his refers to, focus on the umbrella held by that person, and then be able to respond back with the natural language answers, such as his umbrella is black. A human might have another follow-up question, what about hers? Note that this is a more complicated reference. Not only does the model have to understand which person the word her refers to, it has to keep track of the object being talked about from dialogue history, which is the umbrella in this case, focus on it, and then respond back with the answer. Hers is multicolored. The human might have another follow-up question like how many other people are in the image. To answer this, the model has to keep track of how many people have been talked about in the dialogue history so far, be able to convey uncertainty, and then respond back appropriately. Like I think 3, they are included. So why do we want to study this task of visual dialogue? So there can be multiple applications that you might think about. So first and foremost, if there's a robot that's in some sort of a hostile environment, we might want to interact with it in natural language and ask questions or convey instructions. So something like, is there smoke in any room around you? Yes, in one room. Go there and look for people, and so on. It's also obviously useful to aid visually impaired users. So for example, here, somebody's friend is uploading an image on a social networking website, and then they're able to ask questions to this intelligent agent. Great, is he at the beach, and so on. It's also useful for situationally impaired users, where there might be so much visual data that it's not possible for a human to see through all of it. And so if you have a natural language interface to sort of query it more effectively, then that's useful. So concretely, the task of visual dialogue is that given an image, a dialogue history consisting of a sequence of question-answer pairs and a follow-up question, the task for the machine is to predict a free-form natural language answer. And the way we evaluate models for this task is that given 100 answer options consisting of nearest neighbors, popular and random answers from the data set, the machine is evaluated on how well it ranks the ground truth answer in that list. And so to start studying this problem, we began by collecting a data set of human-human dialogues on Mechanical Turk. So one of them is the questioner. The questioner cannot see the image. The other is the answerer, shown on the right. The answerer can see the image. And the task is for the 2 of them to talk to each other for a few rounds, and for the questioner to build a mental model of what this image is. So for example, here the questioner asks, is the man wearing a helmet? The answer might respond, no, he does not, and so on. And so I would like to point out that setting up some of this interface took like some heavy lifting, because Mechanical Turk is not naturally set up to support multi-user hits. So we had to maintain a queue of users, pair them up in real time, and so on. And the code for all of this is open source.
Yeah. What's the goal for Turkers to have reasonably well-phrased and well-meaning questions? Just trying to build a mental model of an image seems a little vague to get Turkers.
Yeah, so I think if we had an evaluation step at the end where we actually made them pick an image from a pool or something, then that would have made this a lot more concrete. So I completely agree with you that it is a little vague in that regard. But we do observe that even if we give them just an instruction that you need to ask questions to be able to figure out what the secret image is, they seem to be doing a reasonable job at it. Yeah.
What's their incentive to continue the conversation?
So you mean like to continue talking for 10 rounds or something? So as in, it's just the pay, I guess. Otherwise, their work will get rejected or they'll be blocked from.
Okay, so if you need like 5 questions from you.
Yeah, so we ask them for a 10-round dialogue, yeah.
Okay.
Yeah, so they're free to talk for more than 10 rounds, but whenever they hit 10, they can choose, they can submit the hit. Yeah. So in total, we have dialogues on 130,000 images from Coco. There's one dialogue per image, and each dialogue is 10 rounds of question answers. So in total, this is 1.3 million dialogue question answers. And all of this data is publicly available. Coming to models, in our initial work, we had a few baseline models. So we had 3 kinds of encoders, 2 kinds of decoders. I'll talk about the decoders first. So the generative decoder, at training time, it's maximizing the log likelihood of the ground truth human response, so it doesn't get to see the other candidate responses. For evaluation, because our evaluation is in a way such that we want the model to return a ranked list, we rank those options by log likelihood scores that the model assigns to each of those options. The discriminative decoder, even during training, it gets access to all of these options. So it can pick up on biases to tease apart the ranking between those options. I'll go over one of the encoders in detail. So the memory network encoder, this is building on Jason Western's work. It's a fairly straightforward model. There's an image which is encoded with a VGG16 CNN. There's a question that's encoded with an LSTM. And each round of dialogue history is independently encoded with an LSTM. To get a fixed size representation. We then compute attention over these rounds of dialogue history conditioned on the image question embedding. We combine those features, and then we pass it to the decoder, which might be a generative or a discriminative decoder.
Yeah. So when you use attention, you lose the order, right? So
yeah. So in this particular model, it doesn't matter whether this was round 1 or this was round 5. But for some of the other models we tried where we were reading this through an LSTM and then computing attention on top of it, that does keep track of order as well. Yeah. So this model doesn't take care of order, yeah. Yeah.
So I'm sorry, I might have missed this in an earlier slide, but you mentioned that you have 100 options.
Yeah.
So for each round of dialogue, your dataset has a correct human provided option and 99 wrong options.
Yeah.
And those 99 were created how?
So by looking at nearest neighbor questions to that question and just using their ground truth responses and random and popular answers from the data set. So it's a mix of those. Yeah.
Yeah.
Nearest neighbor questions in terms of what word similarity?
In terms of this was, I think, glove embeddings of the entire sentence, so average glove embeddings.
And then do you end up with false positives though, right? So presumably
Yeah.
a bunch of the time.
Yeah, so there are multiple options in this list that might be relevant for, that might be correct for a particular question. So I don't have that on my slides today, but we have collected additional annotations for a part of the data set where we are now showing humans this list of 100 answer options in like a reasonable interface where they're not just bombarded with options. But we have asked them to mark all relevant options, and then if we do it, if we get annotations for each list from, let's say, 5 users, then we know that, okay, this particular option, so there's a spectrum there, right? Some options might be more correct than others, so we have some of those denser annotations as well for part of the data set. But yeah, you're right, there are some false positives as well. Okay. Yeah, code for all of these models is also available. We also have a demo that's up on demo.visualdialog.org where anybody can upload an image and talk to this chatbot, which is based on the memory network encoder that I just described. So for example, here, it begins by spitting out a caption, a large building with a clock tower in the middle. You can ask, where is this? Looks like a city. Are there other buildings? Yes, and so on. Just to give you a sense for numbers, I won't go over this whole table in detail. The memory network encoder performed best at the time of that paper, and it was getting a mean reciprocal rank of about 0.6 and a mean rank of about 5.5 for the discriminative decoder. So what this mean rank number means is that that's the mean rank of the ground truth answer in this list of 100 answer options. And there's, of course, been work from our lab as well as other labs which have done much better at this task, and they have better numbers. There's also been concurrent work from folks at Mila who are also studying this task of visual dialogue, but the task definition is slightly different, where they have binary questions, and the task is to discover which task is to figure out which object one of the workers is looking at, for example. Let's look at some of the qualitative results. So these are all questions from the data set on the validation set, and the responses are predictions from our model. So for this image, is the bottle open? Yes. Red or white wine? Red. Is there only one glass? And so on. For this image, what color is the building? Brown. What color is the clock? Black and white. Is it a digital or analog clock? Analog, and so on. Here's another example. So what color is the cat? Orange and white. Is the cat on the floor? Yes. What is the cat on? I can't tell. So there's a clear inconsistency here. It was able to tell that it was able to respond with a yes to a cat on the floor, but it can't tell what is the cat on. Moving on, can you see anything in the mirror? No, just the cat and the cat. So it says cat twice, presumably because there's a mirror and it's seeing two heads of the cat and so on. So some of this, so this is like a popular failure mode in the that sort of emerges when we train models in a supervised manner on this data set, that these models often spit out generic responses like can't tell for a whole bunch of questions. And what we believe, the reason why this is happening is that these models, they're basically artificially injected at a particular round. They're looking at the ground truth dialog history and spitting out one particular answer, and that's the only supervision they're getting. They're not steering the conversation. So after predicting the answer at a particular round, the next round their answer is thrown away, and they're again given the ground truth human dialog history. So they don't get to see the errors that they might make during training. And there's, of course, a vast space of reasonably relevant, just give me a second. So there's, of course, a vast space of reasonably relevant options or responses that they don't get to explore. Sorry, go ahead.
So the images that you showed us, like the images that you test on, they're on seeing images, right?
Yeah.
What about the questions?
The questions are, so they might, some of them might be, yeah, I would expect a lot of them to repeat from the training set. But there might be some that we don't control for it, basically.
Okay, so you don't have like any stat of like how percentage of them
are not seen in the training set. I do not have that stat right now. But
have you run a model where you have completely ignored the dialog history and just run an end-to-end model?
Yeah. We actually have numbers for that in the paper, and I think I should have it. Yeah, so we have, so these were state-of-the-art models at the time of the paper. So for example, in terms of mean reciprocal rank, they get close to 0.577, 578. Some of the models that take in, so these are discriminative with discriminative decoders. Some of the models that take in the dialog history do better than that.
Because, for example, in the cat image, right? So let's say what animal you see here, cat. Is it on the floor? And so here you know one of the assumptions is that well you need to do some sort of coherent resolution to say what is it mean. But when you have an image with just one animal,
exactly, yeah.
your system might figure this out.
Yeah, and that does happen quite often. That even though there is a pronoun in the question, there's only one salient object or person or animal, whatever. So it is fairly easy to figure that out. It doesn't need a dialogue model to, yeah, with memory to figure that out. Yeah. Right. So in an attempt to fix or at least make these models more robust to some of these issues, in our follow-up work, we had an image guessing game between two agents, a questioning agent and an answering agent. So the questioning agent asks questions and is blindfolded. It cannot see images. The answering agent has access to a secret image. And the task is that these agents talk to each other for a fixed number of rounds, at the end of which the questioning bot makes a prediction of what it thinks the secret image is. Right? So more concretely, there are two agents, QBot and ABot. The environment is the image. And at every time step, every time step, QBot predicts a question, ABot predicts an answer, and QBot additionally makes a prediction of what it thinks the image feature vector is. And the state for QBot and ABot consists of the entire dialog history up till that point, and ABot additionally has access to the image in its state. So if we dive into the model internals, on the left in green, I'm showing QBot's policy. So conditioned on a dialog state embedding, it predicts a question, which is just an LSTM that's predicting the question word by word. That question is passed over to the answering side. The answerer encodes the image with a VGG16 CNN, encodes the question with an LSTM, and has a hierarchical history encoder, which at the lowest level encodes each round of QA as fact embeddings, and at a higher level, there's an LSTM that's going over all of these fact embeddings to build a unified representation of the entire dialogue. And so conditioned on this history encoding, it decodes an answer, which in this case is no, there aren't any. The answer is passed over to the questioning side. The questioning side encodes the question and answer, updates its state, and then has a feature regression network, which basically is a fully connected layer from the history encoding to what it thinks the feature vector should be of the image. And the reward for both the QBot and ABot is computed based on how close this feature vector is to the ground truth image feature vector. And so we initialize both of these models by pre-training on the Visual Dialog dataset, and then we train them with reinforce with this reward. Right, so if you look at some of the, sorry.
You don't pass ratings to the VG16, right?
We do not, that's
So
frozen.
pre-trained
Yeah. Yeah, so if you look at some of the results that come out of this sort of training paradigm, so on the left, I'm showing the supervised pre-trained models. So as I said before, they're often repetitive. They often resolve to these generic responses like I can't tell. In general, the dialogue that emerges in these RL trained question answer bots is a lot more diverse and image discriminative. So for example here, what color is skateboard? It's hard to tell, but I think it's black. Is he wearing helmet? Yes. Is he wearing knee pads? No, no knee pads. Is it day or night? It's daytime, and so on. Here's another example. So again, how old is man? He looks like he's in his 20s. What's he wearing? T-shirt and jeans. What color is his hair? Black. And that sort of repeats for a few time steps. Whereas on the right, where is man located? Looks like classroom of some sort. What is man wearing? Black T-shirt and jeans. Which is obviously wrong, but at least it's trying to give out more information than just saying I can't tell. Are there any other people in picture? Yes, quite a few people in background, and so yeah.
When you're doing RL, it can generate any question free form, right?
Yeah.
It's not pulling from a bank of questions or answers. So how do you enforce that it's human understandable?
Yeah, so I think the only thing that's enforcing this in the way we had set it up in this paper is the fact that we are initializing it with supervised pre-training. There's nothing else in this communication bottleneck that's sort of enforcing it. In more recent work, we have, so if I go back to, so here, for example, there's nothing enforcing any sort of human interpretability on that. More recently, we have tried putting an additional reward here, which is based on like a discriminator, or like a language model, which is assigning how likely this utterance is under whatever, a model pre-trained on the Visual Dialog dataset. That does lead to, as you might expect, that does lead to more interpretable utterances, but that doesn't really lead to a better answering agent on the Visual Dialog dataset or better image guessing performance. So it's, yeah, so that's why like it's not yet submitted, or it's work in progress that yeah, we have a way of controlling this such that the generated utterances are natural language, but it doesn't yet lead to improved task performance.
So if you keep training this, presumably there's a more efficient way for this data set
Yeah.
to communicate, which is not human understandable. Right?
Yeah, yeah, of course.
So they converge to something which is sort of
Yeah. So for example, if we train these agents from scratch with RL, then they do real. So I have the. So this is the image guessing performance in terms of percentile rank of the ground truth answer. So if we train this with RL from scratch, we see that very quickly it reaches close to 98, 99% performance, and the utterances are they're obviously not anything sensible. In fact, in many cases, they're very amusing. So things like if it says zebra thrice, like zebra, 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 then that means a particular image. If it says zebra 4 times, that might mean a different image, and so on. Yeah. Yeah, so the reinforcement learned agents do a better job at this image guessing game. But yes, there is nothing that's enforcing them to stay in this human interpretable ballpark. So the way we check for that, so the way we at least enforced that in this paper was that we were checking val accuracy on the visual dialog dataset, and whenever that started decreasing, we stopped training with reinforcement learning. And we have several other aberrations in the paper where we freeze different parts of the model and evaluate them on this image guessing game. And I'd also like to give a shout out to Nirbhay and Viraj, who are lab mates, who have recently ported over this code base to PyTorch, which probably makes it a lot more accessible. And they've actually done a pretty neat job of it. It's a clean code base. It's very easy to use and so on. Right, so I was going to move on to the third part of my talk, which is on embodied question answering. So if I go back to this example that I talked about earlier, that if there's a robot in some sort of hostile environment, we might want to have a natural language interface to ask questions or give it instructions and so on. But there's actually a lot more happening in this example. This agent is able to take actions in this world based on the natural language input and the visual input that it's getting. And so if we think about some of the challenges in studying this sort of problem, as opposed to visual dialogue on like a static data set, first and foremost, it no longer has access to well-composed curated images. It has to deal with egocentric vision. In fact, there is no data set, right? It's the pixels that it sees, it's getting those by virtue of the actions that it performs in this world. And there's, of course, the additional complexity of reinforcement learning, where it might be performing a long action sequences and getting a single scalar reward, and based on that, it has to decide how well it did at this task. So to study some of these, and of course, it has to understand language to some extent, even though when I talk about our instantiation, the language is fairly simple, it's programmatic. So to study some of these problems together, we introduced the task of embodied question answering, which is that there's an agent that's spawned at a random location in an unseen environment, and it's asked a question, such as what color is the car? Its task is to understand the question, intelligently explore the environment to find the object the question asks about, and then respond back with the answer, which in this case is orange. So for this task, we began by introducing a data set of questions in environments. So for environments, we use House 3D, which is work out of Facebook AI research, and it builds a simulator on top of the SunCG data set. So to give you a sense for what this environment looks like, here's a kitchen from SunCG. Here are some living rooms. So it's actually fairly rich. There's a diverse set of objects, their configurations, rooms, textures, colors, and so on. It's not super realistic, but at least there is diversity, and there is cognitive realism in terms of that the rooms are laid out in a way you'd expect in real houses. Here's what some of the bathrooms look like. Right, so at every point in an environment, House 3D provides access to RGB, semantic segmentation, depth, and a top-down map of the environment. And we use all of these to train our agents that I'll talk about later, but at test time, our agent only gets RGB images as input. So in total, we have 800 environments with 12 room types and 50 object types, and there's no overlap between our training, validation, and test environments, so we are strictly checking for at least some notion of generalization to novel environments. Coming to questions, our questions are programmatically generated in a manner similar to Clever. So we have primitives such as select, singleton, query, and relate that are then combined and executed on an environment to generate a whole bunch of questions. So for example, here, executing select objects on this environment returns a list of objects. Passing that list to singleton filters it to retain objects that occur only once, so as to prune out any ambiguous questions. Then passing that to query location generates a whole bunch of location questions, such as what room is the piano located in, what room is the rug located in, and so combining these primitives in a different order can be used to generate a whole bunch of color questions, such as what color is the PlayStation in the living room, what color is the toy in the gym, and so on. So in total, so for this initial work, we used location, color, and place preposition questions. So what room is the object located in, what color is the object in the room, and what is above, below, next to the object in the room. And all of this data is, of course, publicly available on embodiedqa.org. Coming to our model consists of 4 main components: the vision, language, navigation, and answering modules. Our vision module is a convolutional neural network that's trained in an encoder-decoder fashion. So it's pre-trained for auto-encoding, semantic segmentation, and depth estimation. And once it's pre-trained, we throw away the decoders and use just the encoder as a frozen feature extractor. Our language model is just an LSTM that extracts a fixed size representation of the question. So these modules are pre-trained, we combine them, we plop the agent in the environment, and we sample actions from this navigation policy where it gets a reward for getting closer to the target and a terminal reward for getting the answer right or wrong. And the metrics that we evaluate on, so for example here, the agent's navigation might look something like this. And so given this agent trajectory, the metrics that we evaluate on are how close does the agent get to the target, the improvement in distance to target, the percentage of times it enters or ends up in the right room, and the percentage of times it chooses to stop. And for answering evaluation, we look at what the mean rank of the ground truth answer is in the softmax distribution predicted by the agent. So in terms of distance to target in meters, so lower is better. Adding in question information to our, for example, reactive CNN baseline helps do slightly better. Adding in memory in the form of an LSTM performs slightly better. And finally, the hierarchy helps to some extent as well. And in terms of question answering performance, the reinforced fine-tuning step helps to quite an extent in getting the answer right more times than the supervised pre-trained models. So here are some qualitative examples. So on the left, I'm showing the LSTM baseline. So the question is, what color is the fish tank in the living room? So the LSTM turns, it looks at the fish tank, but it doesn't predict stop, and it just walks right out of the house. Whereas our approach turns, looks at the fish tank, and chooses to stop and gets the answer right. Here's another example. So the question is, what color is the bathtub? The LSTM model turns, it can see the bathtub, but it gets stuck against this wall. Whereas our model turns, walks up to the bathtub, chooses to stop, and then gets the answer right.
Yeah. Why do you think having this hierarchy is helping? Because presumably the LSTM is seeing the bathtub there. So does it mean that the LSTM is spending more of its energy trying to look at the prior actions that one would take if one kept going straight, but you usually keep continuing straight? Is it not looking at the image?
So yes, so I think the LSTM does pick up a lot on just the sequences it has seen during training, which predominantly consist of forward actions. Like it might turn at certain corners, but then once it's turned, it might be in a corridor, and it might have to execute 10 forward actions. So the forward label is basically dominating this distribution, and that is essentially what this LSTM is picking up on. So in the hierarchy, if we just tease these two apart, that even if forward is executed once or 5 times, the higher level model will just predict forward once, then that sort of performs slightly better.
So do you think you're essentially sort of you're deduping these sequences of actions of the same action, like forward just becomes forward?
Yeah.
And so you're just getting closer to a uniform distribution with regards to action spaces?
I do think that's part of the reason. So for example, alternatively, if we had a loss function that just put higher weightage on inflections, like after executing forward 5 times, if there's a right turn, then that should be penalized more if it gets wrong. I do think that'll help as well.
Do you have numbers for ablation of supervision? Like if you remove like top-down view, what happens if you remove shortest path training? What happens?
So we are only using the top-down view in sort of extracting that shortest path in the first place. The top-down view is not fed as it never gets the map as input. But we do have numbers with RL from scratch and with supervised learning, and actually I might have it on one of my later slides, but we do have it in the paper as well. Yeah. Okay. So in more recent work, we have sort of a simple idea to improve this navigation performance a bit. So once again, the example here is that what color is the sofa in the living room? That's where the sofa is. This is where the agent starts. So the idea is that we can break down, we can have a different kind of abstraction for this hierarchy. And the hierarchy here is that there's a master policy that's predicting a subgoal. So for example, first it might have to exit the room that it's currently in. That exit room subgoal gets executed by a subpolicy. At the next time step, it predicts the next subgoal, which is to find the living room once it has exited the current room. That gets executed by the corresponding find room subpolicy, and this sort of continues till the agent finally decides to stop and answer the question. Diving into more details, so the task for the master policy in this model is to predict a sequence of subgoals. So it's just a recurrent neural network that's looking at the image frame, the question, and predicting a sequence of subgoals. And we have a subpolicy that's instantiated before that, the space for each, the action space for this master policy is a space of 64 predefined subgoals. So it's not discovering these subgoals. These subgoals are hand-defined for this data set. And there's a subpolicy that's instantiated for each of these subgoals. And the subpolicy is operating at the primitive action space. So it's picking actions out of forward, turn left, turn right, or stop. And so first exit room gets executed, then find the living room gets executed, and each of these have a different set of parameters. So in total, there are 4 subpolicies. The find room and find object subpolicies take an argument as input. So there's the argument corresponds to either the room name or the object name, and the answering model is the same as our earlier work. So this sort of abstraction, this sort of hierarchy, the reason we picked it is because it lets us train each of these sub-policies and the master policy individually with supervised learning, and before putting them together and jointly training with reinforcement learning. And these sub-goals also induce some notion of intermediate interpretability on what our agent is predicting. So whether it's getting the sub-goal wrong or whether it's just doing a poor job of executing that sub-goal, we now have a way to look at that. Both the master and sub-policies are pre-trained on shortest paths. We then put them together and fine-tune in a manner to what I described earlier. There's a distance-based shape reward and the question answering terminal reward. So coming to results, in terms of change in distance to target, so higher is better. This does slightly better than the model I described earlier. And in terms of question answering performance as well, this performs slightly better than the model I described earlier. Here's what one qualitative example looks like. So the question is, what colors the dressing table? So again, this is in a novel environment that it hasn't seen before. So it begins by predicting the find living room subgoal that gets executed, and it ends up here. It then predicts find the bedroom, maybe because it's seeing the bed, or it thinks that dressing tables are often found in bedrooms. That gets executed. It doesn't really lead to a different room. It just ends up moving a little forward in the same room. It then predicts find object dressing table. So the agent turns, looks at the dressing table, and it gets the answer right. Right, so just to tie everything together, I spoke about, sorry, go ahead.
Are the dressing tables ever not
black? I do think a lot of dressing tables are black in this data set. Like there is a skew, but yeah, there are. It's mostly 2 or 3 labels that the choice essentially comes down to in a lot of cases. So there is a skew, yes.
Is the agent able to walk through walls? So it should walk through like a door.
Yeah. We remove all the doors.
So is that sequence of high-level actions trained with teacher forcing to do it?
Yeah.
And so how is that known for you?
So we just rely on basically a few heuristics. So for example, we spawn the agent at some random location, we compute the shortest path till the target, and then given that shortest path, we can have, because we have labels of all of these rooms and so on, we can chunk that shortest path based on which room it's finding, which object it needs to find, whether it needs to first exit the current room or not, and so on. So it's basically, we have a few rules to specify how to extract these subgoals.
And so how much is the RL adding over just supervising all?
So for new environments, my sense is that RL mostly helps the master policy get used to the errors the sub policies are making. Like if the master policy predicts find living room and the sub policy does a poor job at that, the supervised learning agent absolutely fails because it might assume that the find living room was executed perfectly. It has never seen what this sub policy is doing. It has only seen what the shortest path might be doing. So it just gets better at adjusting to the sub policy's performance.
So sorry, I don't know if we should what T minus 10 and T minus 30 actually correlate to. For
Oh,
in
yeah.
In this image here, well, you can just get like in this room, for example.
Yeah.
If there's like roughly 5 rooms, I guess, in this picture. So like,
Yeah.
does that mean like 20% of the time I just randomly spawn actually where I already needed to be, and so therefore I kind of have already solved the navigation task?
I think I didn't completely. Yeah.
You randomly spawn the agent.
Yeah.
And then right. And so if I randomly spawn in that particular house you have up there.
Yeah.
Then and the answer is in the is right there.
Yeah.
Yeah. Then does that mean that like roughly 20% of the time I can already see or I'm already in the room I need to be, so I don't actually have to navigate that much?
Yeah.
Okay.
Yeah.
So this is like so then when you do the T minus, you have those plots for the T minus 20
Yeah.
minus 30. Does that correspond? Does 10 mean in the same room, 30 means in a different room? Or
Most of the times, yeah. 10 is most of the times in the same room. 30 is either at the edge of the rooms or outside, just outside, and 50 is most of the times outside and sometimes in a different room. So it's in most cases, like there might be exceptions, but in most cases, I would think that, for example, the part here is not getting used at all. Like it's mostly just around this that the agent might, for evaluation that the agent might be spawned. And even that, even that turns out to be pretty hard. Like if we spawn it really far, then the accuracy, at least these, our models get is close to 0, yeah. Right, so I spoke about embodied QA that builds on top of the House 3D environment, which itself builds on top of the SunCG dataset. And there's sort of a clear 3-tier hierarchy here from datasets to environments to tasks. And of course, we're not the only ones studying this. There's work out of AI2 and other places that have a different 3-tier hierarchy. And they're studying a whole bunch of tasks such as point goal navigation, question answering, instruction following, and so on. And this is all very exciting because all of this is very recent work. All of this has emerged in like the past year or so. I wanted to give a sense for what some of the more real environments look like from this stack for those of you unfamiliar with this line of work. So here are some reconstructions from the Matterport simulator. So things look fairly reasonable, but there are still quite a few artifacts in edges, corners, and so on. And so in an attempt to make some of this even more realistic, there's ongoing work out of Facebook Reality Labs. And this is basically a plug for that because I do think it's a really cool environment. But these are all 3D reconstructions, so it's extremely realistic. And if we have a way of training these embodied agents in this sort of environment, I do think it will generalize a lot better and transfer better to actual robots. Yeah, so to summarize this section, I described embodied QA. We have released a data set for this task, and we had a hierarchical navigation policy of 2 different hierarchies. And this is, of course, one step towards what I think an embodied agent that can see, talk, act, and reason might look like. Our data set and code for at least our initial work is available on GitHub. Before I end, I wanted to give a quick overview of some of our more recent work, where the goal is to extend some of these embodied agents to a multi-agent setting, where these multiple agents are now able to perceive, talk to each other, and execute actions in environments. So this is basically what our architecture looks like. So there are n agents. Each agent is looking at some observation and predicting an action and a message. And our specific contribution, what we were interested in, was this soft attention-based targeted communication architecture, where the idea is that in earlier works have looked at how these agents might broadcast messages to all other agents, and at the receiving end, you can mean pool or average all of these incoming messages and then take an action. What we are trying is that what we are interested in is whether adding in some sort of targeting, where the sender decides who to communicate with, whether that helps in improved task performance or not. And it also leads to some intermediate interpretability in terms of who which agent the sender is communicating with. So here's an example on like a toy data set, a toy environment. So this is what the complete state looks like. These small squares are the agents. They're looking at just the 5x5 patch. The task is, at least for this particular case, is for all agents to reach the red region. The last column is showing what the attention looks like. So initially, they're basically just exploring the environment and communicating with each other, but the attention is fairly uniform because no agent seems to have anything useful to say. But as soon as agent 1 reaches the target, the attention lights up till all agents eventually converge on that. So that's kind of interesting. Here's another example where we have 4 agents. The goals are now different for each agent. So agent 1 has to reach red, agent 2 has to reach red, and 3 and 4 have to reach green and blue respectively. So here, before I play the video, what happens is that as agent 2 is already on blue, and agent 1 is going to pass by blue before eventually reaching red. And blue happens to be the target for agent 4. So agent 4 starts listening to 1 and 2 as the video plays. So
does agent 1 know that agent 4 is looking for blue?
Through the communication channel, they are able to convey that, but they don't get as input what the other agent's goal is.
So it means that 4 needs to first broadcast to everyone saying, if you see a blue, let me know.
Yeah, something of that sort.
Have some sort of an idea of is multi-directional communication taking place?
So what's happening here is that the way this targeting works is that it's not just sender level targeting or receiver level targeting, it's both, that both have to predict. So the sender predicts a query vector, the receiver predicts a key vector, and we compute dot product, and that's the attention weight. So the agent that's looking for blue might just encode in its encode in its query vector that I am looking for blue, and the sender, whenever it's on blue, it might start encoding in its query vector that whoever is looking for blue, you should listen to my message. And yeah. So I can play it again. So right at the beginning of this video, 4 starts listening to 1 and 2 as 1 and 2 pass by the blue region before eventually reaching the blue region. So this is very recent work. We have results on on 2 other environments which are slightly more complex, but I think the intuition is clearer in this environment, which is why I showed this one. I'd like to thank all my collaborators from Georgia Tech and Facebook AI Research, and that's it.